Okay, so now we have this instantaneous rate of change formula, and that's given by f of x plus h minus f of x divided by x plus h minus x. And that kind of simplifies down to this thing on the top will stay the same, like so, but then the bottom simplifies down to being just h, because this x and this x will cancel out. Okay, so how do we use this? Well, we're going to apply the formula, this formula here, then we're going to simplify, and then we end up setting h equal to 0. Essentially what this formula is doing is it's using the formula from before. I'll go ahead and put that here. And it is setting x2 equal to this x plus h thing and x1 equal to x. So essentially what we're doing is we're making this gap between x2 and x1 as small as possible. I'll go ahead and put a graph here visualizing that. Okay, so we have that here. And what essentially is happening here is the green dot is this f of x1, and we're making h continuously smaller. And as h gets smaller, the green dot gets closer and closer to our initial purple dot, which is representing x1 in our first example and x in our second example. Okay, so let's take a look at an example of how we could use this right here. Okay, so here in this example, we're asked to find the rate of change of x squared at x equals 3. So eventually what we're going to do is plug in 3 for this x here, and we're going to set this h equal to 0. But first we have to apply these steps. We have to apply the formula, so we're going to go ahead and do that here. We're going to use this simplified formula. Now we want to take our f of x, which is x squared in this case, and plug in x plus h for x here, and x here. We want to do x plus h squared. That's x plus h plugged in to this function, x squared, minus x squared, which is x plugged into this function here, over h. So we want to simplify this by expanding this term right here. So we get x plus h times x plus h, which gives us x squared plus 2xh plus h squared, minus x squared still, that's this term right here. And then this is all still over h. But now notice we can cancel out some terms in the numerator here. We have a positive x squared here, that cancels with this negative x squared here. But now that leaves us with two terms that have an h in them, and we have an h in the denominator. So let's go ahead and cancel that. That gives us this h will cancel with this h, and this will cancel the squared here. So we get 2x plus h. And now, because we don't have h in the denominator anymore, we can set h equal to 0. So that gives us 2x. So this is a little spoiler for calculus. This 2x is actually called the derivative of x squared. And the derivative is a function that gives the instantaneous rate of change of the parent function, which in this case is x squared, for all values that we want to plug in for x. In this problem, we're asked to plug in x equals 3. So here we plug in 3 into x here, and we get 2 times 3 equals 6. So our instantaneous rate of change at x equals 3 is 6. Okay, let's look at one more example. Okay, in this example, we're asked to find the instantaneous rate of change of x cubed at x equals 4. So let's apply these steps first by applying this formula. That's going to give us f of x plus h minus f of x divided by h. Now we want to plug in this x cubed as our function. So we have x plus h cubed minus x cubed divided by h. This x plus h being plugged in here into our x cubed function, like so, and x cubed being our f of x function here. And now we want to expand this term out by using 3 copies of x plus h and multiplying them together. That's going to give us x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. But again, we have some terms that cancel here. We have this x cubed, we have this minus x cubed that are all going to go away. And now again, we are left with only terms that have h in them. So we have 3x squared h plus 3x h squared plus h cubed divided by h. But we can get rid of this bottom h by taking 1 copy of h out of each of these terms. So that's going to make this a 2. So now we are left with 3x squared plus 3xh plus h squared. But now with no h in the denominator, we can set h equal to 0. And this is going to give us just this term, 3x squared. And again, like we said last time, 3x squared is actually the derivative of this function x cubed that we have up here. Now what we have to do is plug in 4 for x, so we have 3 times 4 squared. That's going to give us 3 times 16, which will give us 48. Now before we finish the video, I just want to make a comment about this setting h equal to 0. This only works if the function that we're working with, in this case x cubed, it only works if this is a polynomial, or a function made up of these power functions, so x, x squared, x to the 6th, something like that. If this function is not a polynomial, you have to do something called taking the limit of x as it approaches 0, which is kind of what we did on the graph. If you remember over here, you can kind of go ahead and rewind it, where we kind of squeezed h closer and closer to 0 and made these two come closer and closer to each other. It's a slight difference, and it results in some other different things when you're using trigonometric functions or other transcendental functions like e to the x or something like that we talked about in our toolbox video. If you want to go watch that, it is up on the channel as well. And that's good enough for now.